Alright, good morning everyone. Glad more of you were able to join us. I was getting a little tied up in here. Alright, my name is Nam. This is Halim. Together we represent Soaring Digital. Although we're only a two-man operation, we like to consider ourselves an ambitious team that's constantly on the rise, looking to explore new landscapes. So for today's agenda, we'll be overviewing brief overview about MIPS architecture, register sets, data types, addressing modes, instruction formats, enhancements that we have made to the baseline architecture, as well as enhancements verification. Block diagram overview just pretty much lays out our overall design. So our processor utilizes a hardware architecture. As you can see, there are separate data memory and instruction memory modules, each having individual signal and storage pathways for instruction and data memory. This provides simultaneous access to program memory and data memory.
Alright, so in our simulation of the MIPS processor, we have data memory, instruction memory, and IO memory that is organized in 4K by 8, so it's byte addressable. But in actuality, it can address up to 4 gig of memory. It's stored in the big endian format, which means the most significant bit is stored into the least significant bit in the memory. Next slide, please. Oh, and it's accessed via load store, so you didn't use input, output, or store word, load word. Here's an example of the MIPS register set. The reg file is organized in a 32-bit by 32 register. Important ones are the 0, stack pointer, and return address. The rest are basically used as scratch registers, but they're commonly used for these. And then we have carry flags, overflow, negative, and 0, and interrupt enable. So interrupt enable, if it's not set to 1, then we can't use interrupts. The 0 and negative flags are used for branch operations, so those are kind of important. Next slide.
Okay, before we leave that slide, should be preserved on a call. What does that mean?
So basically, the flags, should they be preserved?
No, I mean, this is all those registers, says yes and no. We preserve them on a call? What's that mean?
They should be stored on the stack, I believe.
Do you guys store them on the stack?
No, we do not.
So what does that column mean to us?
Nothing.
Nothing?
Well, the only thing we store are the flags on the PC register to
Right.
the stack in our implementation.
So why did you include that column? I'm just curious.
We kind of went off a layout that we found, and I didn't really
Okay.
take that out.
Okay.
This. So the MIPS data type, there's two. There's 32-bit signed and unsigned integers, and it ranges from -2 gig for signed to +2 gig, and unsigned from 0 to 4 gig.
Mm-hmm.
Read it out if you guys want. So for addressing loads, we have three main types. There's immediate register and register indirect. For register addressing mode, this mode is utilized when you need to access operands stored in general registers. So for this add instruction, the RS and RT field are your source registers, both allowing for 32-bit operands. And in this add instruction, they'll be added and stored into the destination register RD. For immediate addressing mode, this entails that the operand is a constant within the instruction itself. So for this IType instruction, we have a 16-bit immediate constant that's headed into RS, and the destination register is RT and not RD, and each have 5 bits reserved for those.
So for register indirect, an example is load word. It's kind of like a base plus offset, but basically this is the base address is indicated by RS and the offset before, so you would add that to the address. So the effective address is in the register and not actually just an immediate value. It's utilized for load, store, and jump instructions, and instruction formats. The MIPS divide into three main categories. There's R-types, I-types, and J-types, and they're all 32-bit wide.
So since our bit processor is 32 bits, all instructions are 32 bits wide. For the R-type instructions, the 6 most significant bits, 31 to 26, are reserved for the opcode, but by default they're set to 0, and the opcode will actually be found in the function block in bits 5 through 0. On RS and RT are your source registers, each having 5 bits allowed for 32-bit operands, and your destination register is RD. And then there's the shift amount, which is also 5 bits, and that's only utilized for shift operations. For IType, you have an immediate value that's part of the instruction, so here we have 16 bits reserved for that. And RS and RT are also both 5 bits, bits 25 to 21 and 20 to 16. And then we have your 6 bits for your output.
So for J-types, we preserve 6 bits for the opcode, which is 31 to 26, and then we have a 26-bit address. That's about it. So for enhancements, we did barrel shift. So barrel shift left, barrel shift right arithmetic, rotate left, and rotate right. Here's some examples. Barrel shift right by 4. You just shift over 4 zeros in, and you take out the last 4 digits and move everything else over by 4. Barrel shift right arithmetic is different. You put in 1s in the place where you shifted in, and everything else is basically the same. Rotate right. Unlike the others, we actually preserve all the bits, so none of the bits are lost. And when you shift over, you carry over the 4 bits over here.
Okay, let's stop here for a second. That's an excellent slide, helpful. The MIPS SRA instruction, shift right arithmetic,
Yeah.
isn't that considered a barrel shift type shift? I mean, in other words, the shift amount says 4.
Yeah.
So I say SRA 4, 2 registers, comma 4.
And
Is this a different instruction than that?
in our original implementation, we didn't pass in the shift amount, and we just shift everything over by 1 for original.
But I'm saying, do you have a special opcode called barrel shift arithmetic that's versus the shift right arithmetic?
Yes.
Yes.
Why? Because shift right arithmetic does a barrel shift by definition.
Yes.
So in other words, when you get that opcode, you're supposed to shift by the shift amount in the instruction.
We would have to fix that then in our
Yeah,
implementation.
or you'd merge the two.
Yeah.
Because SRA is a barrel shift, and logical shift left is a barrel shift, and logical shift right, they're all barrel shifts. So I know I didn't bring this up on Monday, but
Yeah, good.
I wasn't clear if it's a new opcode or it's
Yeah,
just
these-
it's just implementing the SRA using your barrel shift unit. Yeah.
So here's our code. Basically, yeah, they're basically all similar to the regular shift left, shift right, and rotate. I did kind of a special way. Instead of a bunch of case statements, I ordered shift left and shift right together to get the rotate.
Good job.
And next slide, we'll go to the enhancement verification. I loaded 5 registers with these values: 5A, 5A, C6, C6, 1, 2, 3, 4, 5, 6, 7, 8, FFFF, EEE, ABCD, I mean AB, AB, CD, CD, 800, 5A, 5A. Here, I'm doing a shift left, shift right arithmetic, rotate, and rotate left, and it's in a loop. So it's gonna loop 4 times. So total is shifting 16 times for each of these operations. So here in register 1, initially it was 5A, 5A, C6, C6, but now since it's shifted left 16 times, it's only left with C6, C6, and then zeros.
Mm-hmm.
And same for 1, 2, 3, 4, 5, 6, 7, 8. The 5, 6, 7, 8 was shifted out.
Right.
Register 3 was our rotate. So it's rotated over, right? So that goes to the left. And 4 is rotate left. So the ABAB goes here. And then 5 we're using for shift right aromatic. And we're pushing in 1, so they're all F. And then we preserve the 800. Yeah, and we had a pass by just to tell us we got through the loop correctly.
Hold it on there. So just to be clear, this goes back to that same question. In your assembly language here, we don't see the machine codes. You've got those MIPS instructions, SLL, so it's not a, you don't have barrel shift.
Yeah.
So it actually is just
I
using
used that and then I edited the machine code because I did it in Mars.
Yeah.
And then I edited the machine code to
So
our
did you
output.
use the 1E key and then put the output somewhere else?
No, I mistaken the 1E key and I was confused, so I kind of...
You just made up another opcode that wasn't
that
used?
was something
Okay,
that we didn't want.
okay.
So this is the block diagram that showcases our entire design. The CPU test module basically just provides system clock and inserts reset for testing purposes. It jump starts the control unit to start the state machine, start fetching and executing instructions just for testing purposes. The rest of the CPU module consists of the instruction unit, instruction memory, data memory. The control unit is what generates the control words for the control signals for the other modules. And here we have data memory and I/O. On the next slide, it shows how everything is connected together. Everything's linked with the 32-bit buses. The address for the I/O and data memory, although they are 32-bit wires, we're only using 12 bits for our simulation for the address. Data memory has chip select for reading and writing, whereas our I/O just has read and write stroke. But it also has interrupt acknowledge and interrupt request, which goes to the control unit. And that's not illustrated here just for simplicity reasons.
Why doesn't the I/O have a chip select?
In our implementation, we took it out because we just had a register, but we did implement another register, like the DY register, and we made an IO register. And
So you also created a separate bus?
Yeah.
Like ION?
Yeah.
Okay, that's how you could get away with that. Yeah, if it was tri-statable, you wouldn't, same thing. We wouldn't need to do that.
So,
Okay.
So here's an example of an instruction unit. Basically, these are the jump address and branch address, and then PCN. We're using IRL 25 to 21 for S address, 20 to 16 for T address, and 15 and 11 for D address. And then we have a sign extension for immediate instructions. Here's the integer data path. The major changes that we made were we had the T address mux, S address mux, and of course, as stated, the ION line. So T address mux, we're selecting 29 for the stack pointer, so we need to use it to reference the stack. And also S address, just for good measure, in case we needed to use either of them. Here's IO in register, so this is from the IO output, and we're putting it into the YMUX also, and there's PCN. And we also have flags out when we read it in to the DN, we also read it out to the MCU. Okay.
This is our entire design. Most of the changes that we made have already been covered. The only thing that we haven't talked about was we added an additional MUX for the I/O and data memory, and that's just taking in the present state flags in case of an interrupt. That way we can save the flags and NPC and check for an interrupt. But everything else is similar the same to the baseline structure.
Great diagram to see it all laid out.
We're working on that draw I/O skills. That's about it. Final questions? Thank you.
Excellent.